So first up is Rich Wolski, who is also a professor of computer science at UC Santa Barbara and was one of the key founding members of the computing effort at IEE. He's going to talk about their open source cloud computing software. I think, as we have all probably heard, there's been quite a lot of attention paid to cloud computing as sort of a scalable solution to provide more energy efficient computing. Thanks.
Good afternoon, everyone. Welcome to the afternoon session. Thank you, Fred. Thank you for allowing me to speak to you today. Yep, I'm Rich Wolski, and this is actually a talk about some work that started as research in my research group at UCSB, the computer science department, and then almost against my will commercialized itself with me as its chief technology officer. So let's go back. This is April 2008, so this is almost 2 years ago. I do distributed computing research. I've done it for a long time with the National Science Foundation, and we build infrastructure. Our stuff is very empirical. We build systems that scientists, chemists, and biologists use to get their chemistry and biology and physics done. So it's very empirical. And along about 2008, I started seeing a lot written about distributed computing in the popular press, not the academic press, but the popular press. And this is very exciting. You're working in a research area for many, many years, and suddenly people are excited about it. And so I started reading what they were writing, and I found I understood absolutely none of it. I'm qualified to read papers on distributed systems, and I didn't really understand what people were saying. But 527,000 of them were saying something. If you looked at Google at the time and typed in cloud computing as I did, if you do that today, it's 23 million. So that's a big jump, right? The thing that came before this was grid computing. I've done grid computing research. It took about 15 years before we saw this kind of uptake. And if you want some idea of scale, that's Barack Obama, right? Now, those numbers are actually shocking, right? I mean, according to the folks who started Google, this is the mind of God. And the mind of God is that, is only twice as interested in Barack Obama as in cloud computing. So this is a big deal. And credit default swap is not interesting at all, which is kind of depressing. So if you're a researcher and you see this, you get excited because it means that there's a lot of work to be done to try to develop an understanding of what's happening. And so that's where we started. And this is what we understood. This is cloud computing. And I put this slide up. This is a very controversial slide. Everybody, when I do this now, has a strong reaction to it. And so it's OK. I'm used to it. But really, this is the dictionary definition of cloud computing today. This is what people mean when they say cloud computing in common usage. It's not what cloud computing is going to be tomorrow. Tomorrow, it's going to be something different. This is an evolving term. It's a very, very dynamically changing technology. But right now, this is where it is. And it's easy to understand. Start at the bottom. At the bottom, what we have is a picture of a data center run by an e-commerce company. The e-commerce company in question here is Google, but you can think of this as being a common facility run by any very large e-commerce company. Google, eBay, Amazon, Yahoo. These are companies that sell things over the web. Right? And what they do is they put in these big data centers. Each of these buildings is 100 meters by 50 meters by 4 stories. And they're just jam-packed full of machines and disks and power supply units and network units. Right? So a lot of power going into this. And this is actually on the Columbia River Gorge because 5 miles upstream is a power plant. And the rumor is they've contracted for 120 megawatts just to run that facility. There's a lot of power going into this. Okay. Long about 2004, Amazon.com, which has data centers very much analogous to this all over the world, discovered or thought about or somehow conceived of the idea of renting out space in these data centers in the way that they rent or sell everything else. Amazon sells you everything. They sell you books. They sell you digital cameras. They will rent you movies, Kindle books, whatever. They have huge web service infrastructure scattered all over the world that is designed in the most zero-touch automated way to take a credit card click, run it down to a distribution center, and send you back whatever it is that you've purchased. Right? And they do that in the way that involves the fewest number of people in that cycle, because that's how you keep the margins low. It's a very low margin business. And the more you can automate the delivery of something through the web, the cheaper it is to run your business. So they said, wow, gee, we're selling everything else. We might as well rent time in those data centers. There's a technology called virtualization, which makes it safe to do that. Before virtualization, you couldn't really pull this trick off, because if I rented to you and I rented to someone who didn't like you, they might, there might be a conflict there. But virtualization gives you this kind of encapsulation notion, this safety notion. And so they said, great, we've already got the web services in place. They're very scalable. They run all over the world. We're just going to start doing that. And by the way, because we have to do this so efficiently, we can rent this at a very cheap price. Right? Amazon is keeping its margins low by running this data center and its other data centers in an extraordinarily efficient way. And so they can offer a very, very good product at a low price point. If you buy that as the model, then really cloud computing becomes obvious. There are a set of web services. They must be scalable. There's virtualization that's providing an isolation framework. And then there are users. Okay? And when the users essentially go through these web services, they have certain expectations. First expectation is that things are transactional. When you buy a book from Amazon, Amazon doesn't say, I've got 40% of the words in the book. I'm going to ship you 40% of the words. And then you can try again at 12 o'clock, and I'll ship you the other 60% of the words, and then give you some assembly instructions. Many distributed systems are designed this way. That's not going to work, right? And it's not going to work because it's too complicated to have all of the possible assemblies that you could give back. So cloud computing is transactional. You make a request of the cloud. Either you get the answer back or you do not. It's unambiguous. And that's hard to do at scale, right? It's a technological challenge to provide that kind of scale on the front end of the system. The other part of this that comes out of cloud computing is the notion of a service level agreement. It's really a misnomer. But when you buy a book, before you buy it, there's a description of the book. It says how many words are in it, how many pages, who the author is, what the publisher is, hardback, so on and so forth. This is a description of the quality of service you will receive from the book when it's delivered to you. When you know something about what you're buying. And that's, again, provided zero touch, right? It's automated. You don't talk to a person to hear that. So in this case, you need the same kind of description for whatever it is you're renting. There are service level agreements that users consult when they make rental or purchase decisions. And those have to be automatically exported through the web services. And this has to be done at very, very large scale. Cloud computing. It's not that complicated. If you see cloud computing, what you should be thinking is automated e-commerce rental of infrastructure. Okay, so we discovered that by studying this in the same way we study other things. We build systems and then observe what they do. And so we decided, wow, the way to figure out this and other things about cloud computing is to have a system that we could run in our lab, not inside Amazon or inside Google, because Amazon and Google are a little reluctant to let my graduate students use their infrastructure directly. So we needed an open source infrastructure for our lab, which we invented. One of the engineers is a photographer, and he was out thinking about this, and he said, we should call this Eucalyptus, because there are eucalyptus trees all over Santa Barbara. And I said, no, we should call it Eucalyptus, because it stands for Elastic Utility Computing Architecture, linking your programs to useful systems. I'm old enough for where systems have to be acronyms, and this was clearly an acronym. Any way you slice it, we did it, and we built it as web services using open source. But then we run into this problem, which is that many other researchers were interested in this discipline. And we would say, OK, so here's what we've discovered about cloud computing. We would say this in the academic fora. And they would say, no, that's wrong. You're not really building a cloud. And I would say, well, OK, what are we doing? And they say, well, we don't know what you're doing, but you're not doing what we're doing, and we're building a cloud, therefore you're not building a cloud. And so academics start out technical arguments this way, and we did it for about 3 or 4 months and found it very unproductive. So we said, well, how about this? How about we find something that everybody acknowledges is a cloud? Undeniably, 100%. You cannot in public say it's not a cloud. And then we emulate that. If we can do that, if we can emulate what everybody agrees is a cloud to the point where a person or another program cannot tell the difference, then we know we have built at least one cloud. Okay? That's called a Turing test for those of you who are in computer science. And the Turing test for cloud was Amazon AWS. Everybody agreed that Amazon had built the first cloud. And so we said, well, we're going to make our thing do what AWS does to the point where you can't tell the difference. And then we know, undeniably, we have built at least one cloud. And then we built it for an academic environment so that it could just lay on top of whatever was there. You can't go at UCSB, even if you're in charge of the facilities, and tell your facilities people, please uninstall all the software so I can do my research. That annoys the other people who are using that software at the time. So you have to be able to overlay what's there. And then those people actually are overworked and underpaid. And this is true across the industry, and it's because IT is a cost center. So you try to run it as lean as you possibly can. But you know, anyway, we knew that we had to make system administrators our friends if we wanted this to succeed. So our goals were to foster this understanding, but very, very quickly, we heard of a lot of different uses for open source cloud computing. One was a lot of science groups at UCSB were interested in whether they could use Amazon's AWS. And they said, wow, gee, you know, they called me and said, if I ran this on my cluster in my lab, would this work just like AWS? And I said, yes. And I could see what my applications do? Yeah. Great, can we have it? So almost immediately, there was pull out of the project by people who wanted to figure out something about cloud computing. And then there's this idea, can I run partially in AWS and partially in my environment and optimize, right? I want to save some power, I want to save some money, or I've got some private data that I want to run locally. You can do this kind of hybrid notion. That's absolutely true. And you know, the community really needed something like this. There was a lot of interest and not a lot of engineering. What it isn't, though, it is not a replacement for AWS. You can't take something you download from the web as a series of files. It's probably about 50,000 lines of code, and run it on 22 data centers around the world, right? That software is designed with the data center's actual physical hardware and physical infrastructure in mind, and this is designed to run on your laptop, as well as in your data center. That kind of portability demands that you give a little bit away in scale, and we've had to do that. So this is not a replacement technology for AWS. It's something that complements AWS inside the data center. Okay, another thing that happens, and this is more context, is immediately, though, we started coming up with layers. So what we do is called infrastructure as a service. And this is the idea that you can rent these virtualized machines, if you will, across the network. Up the stack a little bit is something called platform as a service. This is really where Google lives. This is Microsoft Azure and Force.com. And it's a richer environment in the sense that there's a programming language now associated with it, but it's a more restrictive environment in that it's not really a machine. You can't make it do anything you want. You can only make it do what the platform says you can do. And then the part that everybody gets excited about is software as a service, which is like Gmail, where you don't even run programs. All you do is give it your data, and then it operates on the data. So the way to think of this is, I upload my data, right, software as a service. I upload my data and a program, but a restricted program, platform as a service. I upload my data, programs to run on it, and virtual machines, infrastructure as a service. And we do the latter. And the reason is because it's very flexible, right? That you can use multiple technologies at the same time. That's very important in modern application design, particularly at scale. You can run old systems, right? You can't do that in platform as a service, but you can do it with infrastructure as a service. It's very transparent because you can look down beneath the application into what the machine is doing. It gives you some QoS control, and it allows you to avoid this notion of lock-in, which is if I use platform as a service, if I'm using a particular programming language, and then that platform changes, or the owners of that platform change their rates or something, I'm kind of stuck with it. If I use generic virtual machines, I can avoid the possibility of being locked. So that was it. And another thing that comes up immediately was, well, how well are you doing, Rich? Is this thing really like Amazon or not? And so we did a lot of benchmarking, and this is an inverted CDF. The way you read this is 60% of the things that happened took 10 seconds or less, and that's because here at 60%, the line crosses 10 seconds. So this is image starts. If you start 4 virtual machines inside Amazon and the same virtual machines inside Eucalyptus, 60% of them in Eucalyptus take 10% or less. 60% of them in Amazon take 20 seconds or less. And you think, wow, Eucalyptus is beating Amazon. Well, not really. This green line is on a machine that's about the size of this podium. The red line is on a machine that's the size of North Dakota, right? It's hard to make North Dakota behave like the podium. And so this is really a testament to how fast Amazon runs. The important thing, though, from our perspective, is the shape of these curves. Because these curves have similar shapes, statistically speaking, it indicates that we're governed by the similar dynamics. And that means that Eucalyptus is not an inherently broken implementation. It's being controlled by the same underlying randomization factors that Amazon is. Amazon is just shifted up because of its scale. So it's a pretty high-quality implementation. One of the things that you do when you're an academic is you look for impact, right? We count how many times our papers have been cited or how many times we're invited to speak. we get a little bit of a heartbeat when you stand up a Eucalyptus system, if you allow us. We have a separate website where you can go and get some tools to help you with Eucalyptus. And when you go and get those tools through our UI, we get an IP address. These are the Eucalyptus starts since July of last year. And there's a lot of them, but the remarkable thing is where they are, right? There's 2 poor souls in Iceland. That's the Azores, the Canary Islands. I mean, if you do open source, you can have tremendous impact in a very short amount of time, right? That is way more than my papers have been cited. I love my papers, I love my research, but I cannot point to a diagram like that and give you an analogous reading of the impact that my previous research has had, and I can here. And that to me is really a compelling reason to do this from a university. Okay, so what does all this have to do with power optimization? All right, that's cloud computing. And I'll try to do it in this, this little cartoon. Today, if you are running a large organization and you have, down here at the bottom, a collection of machines that is in your data center, and at the top, your organization has some users, there is a sub-organization in between the users and the machines called IT. And that organization's job is to provide access to these machines for those users. Notice all of the requests, all of the things that the users want to do to the machines in terms of reconfiguring them, in terms of allocating them and deallocating, has to go through this organization. It's very labor intensive. Notice also that in a normal business, this is a cost center, right? These people don't make money for the business. Those people make money. If this is a bank, an investment bank, those are the people who are out there generating revenue, right? These are the people who are spending the revenue. So this organization is very, very cost sensitive. They're constantly trying to cut costs. And consequently, it's usually made up of very unhappy people because they're working really, really hard with the fewest possible resources. And this is true almost universally. What cloud computing does is it replaces all of that with a set of scalable web services that are automated. Right? So now your users, rather than talking to a bunch of unhappy system administrators via memos, talk to web services using a set of automation tools. And there is a staff. It's just smaller, right? Because they have to maintain the cloud and maintain the services. But because much of what they have to do has been automated, you can shrink the size and increase the efficiency of the organization. Furthermore, these services are irrevocably in charge of what happens on the infrastructure. It's fully automated. It happens at machine speeds. So you can do things like monitor power consumption and set virtual machines up based on what they're using so that the system makes good decisions about where those are. If your users are entitled to put VMs or machines, applications anywhere in the data center, they might not be optimizing power. But this set of services can be programmed to do that automatically. So you can get tremendous efficiency gains, both in terms of the IT organization, which is a really, really big cost savings for the company, but also in terms of the way that you use these resources, in terms of efficiency and power consumption, things of that nature. I'm just going to conclude by saying thank you. You cannot do this, which is to go from research to a startup company in a year without support of your department. University of California, Santa Barbara is the most underrated computer science department in the country. I believe that wholeheartedly, although I am a little biased. The National Science Foundation paid for the research that made this possible through the VGrads project. This is a long-standing 8-year research effort that culminated in this work by many, many researchers. This is just our part of it. And as of last May, as of a year ago, we abandoned our friends in the public sector and found some new friends in the private sector. They're equally enjoyable to work with, a little tenser than our NSF colleagues, but no less enjoyable. Benchmark and BV Capital, that's me. I'll stop, and thank you for your attention this afternoon.
Great talk. I'm Shaheen from Lux Capital. We're a venture capital firm as well. And I was curious to know if your platform is useful for larger organizations that do hosted IT solutions like IBM and HP.
Yeah, very much so. The customers we have, and we actually have customers, they tend to be, towards the top end of the Fortune 100 or Fortune 200, whatever you want to call it. And tech companies, financials, entertainment, manufacturing are the big consumers at the moment, for various reasons. So yeah, cloud computing, as we do on-premise cloud computing. We do cloud computing inside a corporate data center rather than as a service, as the way Amazon or Google does it. And that self-service and automation component of it makes it very attractive to companies when they're looking at retooling, say, the next 5 to 10 years of their IT strategy. The automation just makes it a lot cheaper for them to do. So companies with large IT tend to benefit from this. Okay, thank you very much.